So Mohammed, let's start with you. I want to get to your current role, but first, can you share a bit about your background? I saw that you've been on the Arduino board, you spent time at Broadcom, and you even worked on Zigbee at Ember. So a great mix of compute, connectivity, systems design. Tell us more.
Yeah, no, thanks, Austin. Great to be chatting with you. I started as a software engineer. I had this kind of concentration in data communications. A couple of years, I worked at those old infrastructure companies, Lucent, and Nortel, and kind of did some of that. I went on to work at a little startup that was working on mesh networking because I thought wireless was cool. This was back in the early 2000s, and that took me to Europe for a while, and then eventually took me to Broadcom, where I got to do all sorts of fun stuff, everything from Bluetooth and Wi-Fi through to GPS, and I even started a custom ASIC business there, which went on to build custom ASICs for the likes of Apple. In 2018, I joined ARM. I kind of went back to my infrastructure roots, and have gotten into the compute side of things in a big way. It was a great time to join. Obviously, ARM's been on quite the trajectory since 2018 within infrastructure, and excited to have been played my little part in it. So
Nice. Okay, great. So yeah, you have a full stack background from software to networking, all the way down to custom ASICs and hardware.
that's right. That's right. I kind of a jack of all trades, not an expert in anything, but kind of dangerous enough in a lot of different areas.
There you go. Nice. Cool. And then, of course, today, sort of the big picture is AI. And very curious to hear your perspective from where you sit at ARM on AI data centers. Obviously, those are really driving today's compute needs. And nowadays, we're not talking about flops or about chips, but really about like gigawatts of deployed power. So all the
Yeah.
conversation is about how much can you get out of this gigawatt of power? So curious how you see ARM approaching this shift, this sort of macro trend shift, as power efficiency, rack scale integration are key constraints.
Yeah, it's a really interesting question, right? Because and you kind of hit the nail on the head when you said it's not about sort of the amount of compute, because really the amount of compute needed is just sort of unfathomable, right? I mean,
Mm,
it is sort of impossible to sort of quench the amount of compute that's needed for the sort of aspirations that the world has around AI right now. And then the other thing that's happening is you've got a lot of dollars flowing into AI. And so ultimately, if you look at what the constraint is, it actually is power. It's about like, hey, how do we cram as much compute as possible within the allotted power envelopes that we have available? Because you just can't build it fast enough. I mean, people talking about nuclear power plants and putting data centers in space and underwater, and it's just all about kind of managing that power constraint. For ARM specifically, I think it's actually it's been a real tailwind for us in our kind of Neoverse products and our kind of infrastructure aspirations, and a lot of that is because when you're in a situation where the technical requirements exceed what is possible with off-the-shelf technology, people turn to kind of optimization across the entire stack. So that means optimization of the networking and optimization to the workload and optimization really all the way down to the silicon level. I mean, when data centers started, everyone knows the Google story where it was a bunch of off-the-shelf components in a Stanford dorm room, and that's how the first data centers kind of started. Well, today, whether it's Microsoft or Google or NVIDIA or AWS, they're building full-on racks, and alongside that, they're building custom networking and, custom CPUs and custom accelerators, and they're all optimized for the workload, optimized to eliminate the effects of Amdahl's law, optimized to get as much perf per watt as possible out of that box because they are power constrained. Um, in that environment, being a company like ARM, where we provide lots of different, points at which people can integrate, whether that's IP or compute subsystems, or even off-the-shelf CPUs from partners like NVIDIA and Ampere and others, really what we do is we allow these consumers of compute, whether they're building a networking chip or a CPU or an accelerator, to basically come to us and take bits and pieces, and we kind of enable that and kind of help accelerate all of that investment. And that's been that's been a fantastic place to be, and we're continuing to lean into it.
So it sounds like you're saying that power is the limiting constraint, and ARM is there to help customers. When you're constrained by power, you need to start to optimize for power all the way up and down the stack. And it sounds like you guys are there to help customers at every layer optimize to get the highest performance.
Yeah, that's right. And it's not just ARM, it's really our whole ecosystem. I mean, ARM's a 35-year-old company. We were born in a turkey barn in Cambridge, right? And that first product was building a custom SoC for the Apple Newton, right? So this is a power constrained device, which is, and so this is just a kind of continuation of that legacy where we've enabled this kind of ecosystem to go build those types of devices. And this is the next big problem that we're helping the world kind of go solve.
Nice. Makes sense. So, okay, I'm really excited today to talk about chiplets. That's something I've been writing about lately, and I know ARM is in this space. And so, I guess for our listeners, setting some context, wafer costs in a monolithic design keep rising as the industry is approaching silicon's physical limits. And we know chiplets are an option, is sort of a solution to let designers keep the expensive nodes focused on compute logic and keep everything else, I/O memory, analog, older, cheaper processes. Of course, the problem is only vertically integrated companies historically have been able to pull off chiplets. AMD and Intel, a lot of innovation there and pulled it off. And so, Mohamed, I'm curious from your vantage point, like what has to happen technically, organizationally, for a true chiplet ecosystem to exist, one that's multi-vendor that everyone can participate in regardless of their size and not just like an internal multi-die.
Yeah. I mean, I think it's certainly a super interesting area, and one that we've kind of done quite a bit around. If I take a step back, one of the key offerings from ARM is our ARM compute subsystem, which we really brought to the market about 2 years ago. And around compute subsystems are integrated verified IP that we make available to the ecosystem. And so we put those compute subsystems out there, and then we created an ecosystem around them of partners, everybody from foundries to IP vendors to ASIC providers, et cetera. And what we found is that ecosystem began trying to create chiplets that they could make available to the world based on our compute subsystem. So they kind of just naturally started to do that. As part of that effort, we kind of stepped in and we started to define aspects of what a kind of standardized ARM-based compute chiplet would look like. And, we've had, a bunch of partners kind of adopt that. There's a bunch of chiplets available today based on that. And in fact, just this week, we announced that we're moving that entire effort to kind of standardize some of those chiplet efforts within OCP, because it's really it's broader than even ARM. I mean, this is an industry-wide thing, which is really, really critical for us. Now, I think the idea of a interoperable chiplet marketplace, we're still quite a ways away from that, right? But what you are seeing today is not only are you seeing, as you implied, vertically integrated semiconductor companies reuse chiplets in different products, you're also starting to see some multi-vendor products emerge. So you're seeing these places where, a semiconductor company A and semiconductor company B agree to some common parameters between them to create some level of interoperability. And we think that some of that can be standardized across the ecosystem to just make it that much easier. And that's what the foundational chiplet standard architecture is all about, or foundational system architecture is all about. So, what I believe is that in the near term, we can standardize aspects of how to debug these things, how they boot, how some of the software lands on them, et cetera. We don't have to go define everything, but we can define much of it to make it that much easier. The fact is that building semiconductors on advanced process nodes today can, cost upwards of $1 billion in some cases to build one of these complicated pieces of silicon. And so, when you think about a fully functional AI rack and the amount of custom silicon that exists in that, it's not just about the dollars, it's about the time to market, it's about the risk. this is a way that we can kind of spread that load across the ecosystem and amortize some of that cost so that you can kind of get to those, diverse power optimized solutions that we talked about earlier.
Amazing. Oh man, there's so much insight in there. Let's unpack that. This is so good. Okay, so interestingly, you were saying that ARM, you first introduced CSS and compute subsystems, and so this was more than just someone licensing IP for a CPU. Now, this is, you mentioned pre-validated pieces. Tell me a little bit more about CSS. It's more than the CPU. It's like an entire subsystem.
Yeah. So if you think about what it takes to build a CPU, right? You got to go off and you obviously need the CPU, the actual processor, right? The actual processor IP, and you might lay down 128 of those, or 64 of those, or 256 of those, whatever you want for your particular design. And then you need a mesh interconnect to connect all those things up. And then you might need an MMU, right? And then you might need a bunch of other IPs around that as well. Well, originally when we started in the infrastructure space, we would actually just hand you a spec and say, you guys can go off and build it. And then in 2018, we showed up and we said, you know what, we're going to actually go off and build the CPU, build the mesh, build the platform. And then so we started handing people our Neoverse IP platform. So we would hand them the CPU, we'd hand them the mesh, and they could connect it any way they like. And we still do that. But 2 years ago, we started with CSS, where we actually pre-integrate all those components for them. We pre-validate it. And so now our partners can just take the compute subsystem and add, for example, an accelerator, or they can add whatever custom, interface that they want, or memory controller that they want, kind of that third-party IP or that other IP that they want. What On Total Design did is said, hey, so we've got these pre-integrated IP. Why don't we invite the ecosystem, make that pre-integrated platform available for the ecosystem, and invite them to go off and do that pre-integration of that third-party IP ahead of time. So partners like Synopsys and Cadence pre-integrate their memory controllers or their interface IP. And then, TSMC and Intel and Samsung use those designs as the basis to ensure the performance of their process nodes, for example. We've got ASIC providers who take it through the physical design process, so they have a sense as to kind of what they can achieve. So now when a customer comes to us and they're like, hey, I'm trying to build an SoC and I want a PCIe Gen 6 interface and a memory controller, we can say, great, here's the CSS. You can go to this partner, he's got a pre-integrated interface IP. You go to this partner, he's got a pre-integrated memory. And by the way, we know this is what it's going to look like when it hits the TSMC manufacturing 3 nanometer flow or whatever. Right. So that's kind of the idea.
Gotcha. Nice. Yeah. So it sounds like you're essentially doing more work for the customer so they can focus on however they want to differentiate, or if they're like an end product builder, they can just focus on building what they need to build. So instead of like, hey, here's a spec or here's a CPU, you said, here's CSS, so a lot of the components around it. But even then, I'm sure you saw your customers still had to go do a bunch of work to take it to the rest of the ecosystem. So then with ARM Total Design, you said, hey, let's kind of bring the ecosystem together, ultimately to just make it more turnkey for customers, it sounds like.
It's about making it more turnkey, accelerating time to market. It's about amortizing the cost and the effort and the risk across lots of different designs. If every one of our customers is taking the same CPU core and the same mesh interconnect and the same IP and spending all this effort interconnecting it, why bother, right?
Yeah.
Focus on the differentiation.
Gotcha.
Now, the interesting thing about ARM is that, you can come to us and you can get the discrete IP if you want. You can get the CSS if you want. You can go to ARM Total Design partners and get a chiplet if you want off the shelf now that uses our foundational chiplet system architecture. Or you can go get a full-on SoC from partners like, NVIDIA or Ampere or whoever. So you've got this full-on kind of ecosystem where, as a consumer of compute, you can kind of make this trade-off in terms of how much do I want to invest in terms of opportunity cost, dollars, time, et cetera, versus how much customization I want. And that it's going to be different depending on what particular product you're off building.
Sure, totally. It makes sense. So you're giving customers the ability to sort of jump in at different levels of abstraction and sort of get really dirty or not, depending on just how much optimization they want to do. Now, talk to me then. So this is so interesting with a chiplet ecosystem. So, this isn't necessarily chiplets yet, but you saw your customers taking CSS and then kind of run and trying to not turn it into a monolithic die, but actually start to go down that chiplet route.
Yeah. So what we saw was that, like I said, when I'm Total Design, it had, the foundries, the EDA partners, the IP vendors, and then they had ASIC partners. And what we saw was that a bunch of ASIC partners were like, hey, we're going to actually just go off and build a chiplet and put it on the shelf so that when customers come to us and say, hey, I've got this whiz bang accelerator, we can get them to market that much faster because we've
Sure.
already got a compute chiplet based on Neoverse ready to go. So we saw like 3, 4, 5, 6 different companies doing this at the same time. And we said, this is like fantastic. Like they're solving a problem on behalf of our ecosystem for us, which is really the power of the ARM ecosystem when that sort of thing happens, right? And so what we did is we said, we got those companies together and we said, hey, why don't we standardize certain aspects of this? Well, you guys can choose what shoreline you want and how you want the two things to connect, but we can standardize things like how they're debugged and how interrupts happen and how the software is going to land on them, so that you guys can leverage this across the different designs, and so that when customers come to you, if you partner A has a 64 core design and you partner B has a 32 core design, there's not this massive friction for them to use one versus the other. And that was really how the foundational chiplet system architecture kind of began,
Okay.
which is
Yeah.
now we've donated to OCP.
It makes a lot of sense. So you saw the customers saw the value in taking CSS and turning it into chiplets, and then you're seeing many of them do that. So you kind of try to step in and say, "Hey guys, we should have some standards here to make it simpler." Can you talk a little bit more about the standards?
Yeah, I mean, like I said, I mean, the standard, is purposely, if you think about what is needed for a like complete chiplet marketplace, this idea that I'm going to jump online and buy a chiplet, it's going to show up and just work. There's a lot that goes into that, right? You got to agree to what the interface looks like, what the packaging is going to look like, what the shoreline is, the actual dimensions of it. Um, and then there's a bunch of system level things that you got to think about: how the devices are debugged, how they're managed, what the boot sequence is, what the firmware looks like, et cetera, et cetera. What was clear is that to the extent that within the context of a particular semiconductor vendor, you could design a level of consistency across SoCs in the way that the device is booted, in the way that interrupts happened, in the way that they were debugged, in the way that they were managed. Um, once you kind of come to that realization within a single vendor, now all of a sudden you're like, there's no reason why you can't do that more broadly across multiple vendors.
Sure.
Um, and I think that's really what the foundational chiplet system architecture focuses on.
Gotcha. So, yeah, you're realizing that even for a single vendor, having some sort of standards would help them, like gen on gen, for example. And then at that point, if you could come in as sort of a third party and help align people around it, then it would just benefit the rest of the ecosystem to use the same standards.
That's exactly right.
So, so tell me about. I know that originally there was the ARM chiplet system architecture, and now at OCP you announced a vendor-neutral derivative called the Foundation Chiplet System Architecture. Talk to me more about that evolution.
Yeah, and so I mean, and so like I said, this all started out on Total Design, so it was already very specific to our CSS at first, and it was kind of that's where the focus was. And we've got a bunch of partners now that are building based on the ARM chiplet system architecture. But what we realized was that there are going to be times where there may not be any content in that chiplet. For example, like for an I/O chiplet that wants to connect to an ARM-based chiplet, or there may be cases where you've got an accelerator and an I/O chiplet, and there's no ARM content in the system at all. In order for the ecosystem to truly adopt this, it needs to not be a vendor-specific thing. We kind of came to that realization. And so what we did is we abstracted up a level and we said, hey, what are the broad principles associated with the with what we think the chiplet architecture needs to look like more broadly. And let's move that work into an organization which is kind of really focused on that. And OCP has done a bunch of work on chiplets in the past, and so it was kind of a perfect place for it. I've recently joined the OCP board, and ARM's been committed to OCP since really for many years. We've been a platinum sponsor since 2018, since Neoverse launched, and so this was a kind of natural place for us to go and engage. So you've got the kind of umbrella foundational chiplet systems architecture with us, which is now developing further within OCP. And then within that, we've, sort of below that, or inheriting from that, we've got the ARM chiplet standard architecture, which starts to put some specific things in there, which might be specific to how an ARM chiplet might be built. And we fully welcome and are inviting others to join. So other architectures to join and create their own sort of, similar type specifications.
Gotcha. Okay, so it feels like a very natural progression of we start with IP and then CSS and then ARM total design, and hey, I'm seeing internally in our ARM ecosystem across these vendors, there's just a lot of similarities in what they're trying to build. It would sort of grease the skis if we had some standards here. And then eventually you're getting to the point where it's like, hey, wait a minute, this doesn't have to be ARM, centric. This, you could abstract it, take it, make it more modular, take it another level higher, and keep a lot of the concepts. And so you've got this higher level foundational CSA, and that's part of OCP. And then you've got your own sort of ARM flavor where it makes sense when companies are using ARM content. Totally falling on all that. I guess the skeptic might ask, like, why take it to that step of making what you're building work in for a system that may not have any ARM content?
If you think about the challenges associated with AI and kind of the level of complexity in some of these systems, right? There is so much work to be done that the tent is really big enough for lots of participants. And I think this is a great example of advancing the broader narrative around how we get these systems and the silicon in place to kind of support the aspirations is going to benefit everybody, ARM included. We feel like our value proposition in the market is really tied to our ability to offer, as we said earlier, lots of different points for people to come in and integrate on. And so, getting hung up on whether or not it should be solely ARM or more broadly available was just not the place where we wanted to focus our attention. We think we're all much better off in having an open ecosystem. And by the way, this is not something that's new to ARM. I mean, you've seen us do this before with things like AMBA and other, standards which we've effectively, make available for the ecosystem.
Last question there. You'd mentioned that you're joining the OCP board. So talk to me just a little bit more about that, about participating in OCP and you being on the board.
Yeah. Again, ARM's presence in infrastructure, in 2018, it was, it was we were aspirationally looking to get more and more involved in infrastructure. Our role has grown over time within the infrastructure ecosystem. We actually just celebrated our billionth Neoverse core that was shipped into infrastructure. We expect 50% of cloud service provider CPUs that are shipped this year to be ARM-based. AWS talks about 50% of their CPUs in the last 2 years have already been ARM-based. All the major cloud service providers are building ARM-based CPUs. That's not to mention all the ARM content and all the networking and storage and all the other gear that's out there. So in that world, it was natural for us to participate in something like OCP, where a lot of these standards and decisions are being made, and more broadly, there is this desire to kind of advance the state of the art. The world is building more and more integrated systems, and that's really at the heart of what ARM does and who we are working with, whether that's the big cloud service providers or emerging initiatives like Stargate or otherwise. ARM's right at the heart of all of it.
Awesome. All right, Mohamed Awad, I appreciate this. Let me see. before we leave, anything that you would like to add? What haven't I talked about? What are you excited about going forward? And anything, the mic is yours.
I mean, I just think we're at such an amazing time right now. Like, it's interesting because I told you I started by telling you I started as a software engineer. I, you know, to back then when I started my career, software was such an exciting place, and it continues to be an exciting place. I'm kind of accidentally in the semiconductor business. I'm accidentally in the hardware business. It's kind of where my career led me. But I got to tell you, I couldn't be a more interesting and exciting time than right now, as far as I'm concerned, certainly over my career. And I just think that, given the aspirations and the transformation that's happening both in the data center and in the world at large because of some of these initiatives around AI and otherwise, I'm just excited to be a part of it and kind of looking forward to kind of where it's going to take us.
I hear you. It's a very exciting time. Thank you so much for taking the time.
Thank you.